Hey folks, Mrs. White here. I am the one bringing you your lesson this week because it's Memorial Day weekend. We all agreed that we would do only one lesson instead of two. So hopefully you enjoy. It might be a little bit longer than other ones because you do only have one lesson this week. We're going to be talking about the normal distribution. And I know since you've started this stats unit, you've talked about several different types of distributions. So you've looked at modeling center and spread using histograms, box and whisker plots. You've maybe looked at the different shapes of histograms and box and whisker plots to figure out if it's skewed to the left or clustered, or kind of figured things out by looking at it that way. So today we're going to look at a specific type of distribution called the normal distribution or the normal curve. We're going to start off by just making sure we're on the same page with mean and standard deviation. Then we're going to talk about where does the normal curve come from, talk about this really cool thing called the empirical rule, and then we're going to apply the empirical rule in two separate examples. Then your homework or assignment for this class is going to be two examples on your own, and they're attached to your guided notes for this lesson. Okay? There should also be a link posted somewhere for you on Classroom for that. So let's make sure we're all on the same page really quick with a couple vocab terms. So I really hope as you're seeing the word mean, you're like rolling your eyes at me because you clearly know that mean is the average in a set of data. Okay, I know you've learned that sixth grade self hopefully is like, yes, I remember that the mean is the average. And you would calculate that by adding up all of your data and dividing it by however many data you have. Now, for our purposes today, when we're talking about the mean, I'm never going to write the word mean. I'm going to use the symbol mu, which kind of looks like this, every time that we talk about the mean. So when it's mentioned, you're just going to go right to this, okay? We're not actually going to calculate any means today, but we're going to use means a lot when we talk about standard and normal distribution. We're also going to talk about standard deviation, and this may have been mentioned briefly in the previous lessons, but you haven't focused a lot on the actual calculation. So let's pretend like this was a normal sit and begin. You'd come in, I'd be like, hey, load up Google, let's check it out. What is standard deviation? So let's actually go down. Let's go to Google and let's type in standard deviation. Ooh, it pops right up. So again, we're not going to calculate this. We just want to figure out what the heck it is, okay? So maybe let's look at what does standard deviation tell you, and then maybe how do you calculate it, just so we have an idea. So standard deviation is a number, okay, so it's going to be some number, that is used to tell how measurements for a group are spread out from the average or the expected value. A low standard deviation, so a number that's small, means that most of your numbers are very close to the average. And a high standard deviation means that the numbers are more spread out, so they're further from the average. So it sounds like standard deviation tells us how clustered our data is. If we have a small standard deviation, it means that they're close together or very clustered. If we have a high standard deviation, that means our numbers are more spread out. Okay, so that's what the standard deviation tells us about our data, how clustered or spread it is. Now, because it's a measurement of distance from the average, the way that we calculate it is pretty extensive. So first you'd find your mean, then you take each raw data and you subtract it from the mean and square the result. Then you find out all of those, okay, and we call those the squared differences, and then you add them all up, and then you take the square root of that. So the formula for they have of it is over here. So this would be your data minus your mean squared. This symbol is a summation symbol, so you would add them all up. Okay, and then depending on what type of standard deviation you do, you may or may not divide it by n, which, again, we don't care about the calculation, but I want you to see it's a pretty in-depth calculation that a calculator could do for you. We're not going to go over it, but I do want you to understand that and appreciate that you don't have to do the work, and that you understand it tells us how clustered, if it's low, or how spread out it is, if that number is high. So let's go back. So standard deviation is going to tell us how clustered or spread out our data is. So we'll just call it our spread. Okay, the higher the standard deviation, the higher the spread. Just like mu was our symbol for mean, our symbol for our standard deviation is this little sigma right here, okay? And so that, and you kind of saw it on that Wikipedia link on the side. It's kind of like an O with a little line off of the top of it. And that's what we're going to use for standard deviation. Again, we're not going to calculate these today, but they're part of our normal curve, so it's important that you understand what they are. So Let's talk about why the heck would we need this or see this. So let's say I gave out a math midterm to 100 students, and I don't have 100 students, but I have a lot. And let's say this was our data. Okay, so here's all the test scores for 100 students. I put them in order from least to greatest. So looking at this data, you could probably say, okay, the lowest score was 60 and the highest score was 100. Hopefully you could say, all right, I could make a box and whisker plot of this. I could find my median, my upper quartile, my lower quartile, okay? And that would tell you something about this data. But another thing you could do, and you have done in the past, is you could create a frequency table. So we could look at how many, what the percentage was that people got correct and how many times it happened, right? Frequency is just how often it occurred. It's like our tally marks. So 60% correct on their test would be 1, 2, 3 people. Our frequency is 3. 65% correct. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 is the frequency. Now, this tells us some stuff too, right? It tells us that, wow, the most amount of people out of that 100 people got an 80. Okay, so it kind of tells us our maximum. It can also, or not our maximum, but our most popular, right? And our word for that, if it's the most popular, is our mode. And then again, we can still see our min and our max values from here. Now, if you think about your previous sections, you could take your frequency chart and create a histogram, okay? And this is actually just a bar graph. Histograms, remember, they have to be touching and they should have a span of numbers. This just represents each actual grade earned, okay? So if we take a look at this, we can see, oh yeah, there's our frequency of 3. It only comes up to 3. There's our really popular one, which was in the 80s. This shape right here, okay, this shape where it kind of comes up, whoosh, and then comes back down like this, is the shape of the normal curve. Okay, when things start low, increase, and then go back down and decrease, and it creates kind of this bell-shaped curve. So if you've ever heard of the bell curve, when people talk about grading, this is what they're referring to. Okay, and so this is why we have the normal distribution, because a lot of things fall into this pattern. So testing often can turn into that. Heights, IQ tests, lots and lots of things are what we call normally distributed, meaning that there's low things on either end and it gets higher towards the middle or higher towards your mean. Okay, so let's hop over to your notes and actually take a look at 4 key features of the normal curve. And I might call it normal curve. I might call it the normal distribution. It can be referred to as either or. But there are 4 main things about this graph that it's important for you to know. So the first thing that you need to know is obviously, it's bell-shaped, okay? But it is symmetric. And you should know what that means, right? That means that you could fold it in half or rotate it. And this specifically is reflectional symmetry. So you could fold it right here in half, and the top half and the bottom half are going to be exactly the same. Okay, so they're symmetric, and they're specifically symmetric right about the middle part, and this middle part is going to be the mean. So again, I'm using that symbol for mean, okay? So right here is going to be our mean. Always, every time, right through the middle at that highest part is going to be our measure of center, which is our mean, okay? It's not just the mean though, because when you're talking about something that's normally distributed, right in that center point at the highest part is going to be your mean, but it's also your mode, which is the most often one. We saw that in our bar graph before, right? And it's also actually going to be the median or the middle number in your set of data. If something's normally distributed, all 3 of those occur at this exact highest point. Okay, and because all 3 of them are going to be the same, we're just going to refer to it as the mean, but it's really all of the measures of center, mean, mode, and median. So this curve, it looks like right here it hits 0, right? It looks like it hits the axis, but this curve actually never hits the x. It just gets closer and closer and closer. So it's actually never hitting to this 0. Now, one other thing that's kind of weird to think about is the area underneath this curve, okay? So if I were to shade in everything here, it's going to represent 100%. So if I'm thinking about my example here, right, if I were to shade in underneath this curve, it would represent 100% of the tests that were given to all of my students, right? If I were to look at just this area over here, it would only represent this percent of students, the percent that got from 60 to 65, okay? And I can figure out how many of those people were by adding these up, it would be 13 out of 100. And so that would represent 13% of my people, right? 13 divided by 100 is 13%. So the area under the curve is also going to be related to the percent of people, okay? So the way we can write that is underneath the curve represents 100%, which also equals an area of 1. An area is often related to percentages, okay? As we're going to kind of look at a little bit with some of the problems today. So these are the 4 big ideas. They're symmetric around the mean. The highest point here is going to be your center right here, which is modeled as your mean, your median, and your mode, okay? But we're just going to refer to it as our mu, our mean. These 2 little tails here, and they call them tails, but it's like the little ends here actually never hit the x. They continue getting closer and closer and closer, but they never actually get to it. And that the area under the curve equals 100%, or it has a hole, right? It's an area of 1. So if underneath this curve is an area of 1, okay, or 100%, and it's symmetric, then there's some stuff that we can, or some general conclusions that we can come to, okay? And these general assumptions that we can make are called the empirical rule. So the first thing is that obviously one of our key things to know is that our mu is right at our center, right? Our average is right here. So if that's our mean, then it's clear to say that anything lower than the mean, if this is exactly half, is going to be 50%, right? So from here to here would be 50% of our students, and from here to here would be the other 50% of people, students, whatever, okay? That's pretty obvious, and it's a given. But the empirical rule gives us even more information, which is actually kind of cool. If you come out to this point right here, which is your inflection point, which means it goes from being concave to convex, okay? And if you come out to this inflection point right here, from here to here is actually going to always represent 68% of the people. Always and every time, okay? Now remember, this normal curve, if it is happening at the inflection points, but this value down here is actually related to the standard deviation. Remember when we talked about standard deviation, we found that it tells us how clustered, right, or spread out things are. So it could be really spread out till we get to this inflection point. It could be really, really close to the mean if this is a little bit steeper, okay? So the way that we actually find this value is we take our mean and we add 1 standard deviation to it. And to figure out this number right now, we would take our mean and we would subtract 1 standard deviation from it. So this distance from here to here represents a standard deviation, and from here to here represents 1 standard deviation, okay? So if that standard deviation is smaller, everything's clustered closer together, okay? If this standard deviation is bigger, then this span is really far apart. Now that's pretty cool anyways, right? Like 68% is going to be within 1 standard deviation below or 1 standard deviation above. Well, it gets even more detailed, okay? If we go out 2 standard deviations, so from here to here, okay? So that means we have 1 standard deviation there, we would have another one here, and another one here. So if we were to take our mean and add 2 standard deviations to it, and if we took our mean and we subtracted 2 standard deviations from it, this percent right here goes up way high, right? If you look at the curve, the whole area underneath it, right? If I were to shade that all in pink, that is almost the entire curve, okay? And in fact, if it's 2 standard deviations in each direction, it is guaranteed to be 95% of your data. So you can figure out 95% pretty quick. It's going to be what happens between the 2 standard deviations above and 2 standard deviations below. And then the last one, and you're going to think, oh, Mrs. White, it's going to be 100. It's actually not 100, okay? From here to here would be 3 standard deviations. So our mean plus 1, 2, 3 standard deviations, and our mean minus 1, 2, 3 standard deviations, okay? It's almost everything, but remember, this curve never quite hits the x. This is going to actually represent 99.7 of the people. Okay, so if we go all the way from here, all the way to here, so 3 standard deviations below and 3 standard deviations above, that's going to represent 99.7. Okay, so we have this big idea of 3 standard deviations out being 99.7. 95 would be here, 68 would be here. You can even break this into smaller pieces and parts. If this whole middle section is 68, then I could say from here to here is going to be 34. And then I could even figure out this section from here to here, okay, by doing some subtraction. And that's what we're going to end up having to do, okay, with this empirical rule is we can figure out and set up this curve for the 68, 95, and 99.7, but then we might be able to figure out even smaller, like the middle 34, the upper 2%, or whatever, okay? But we're going to use this idea to kind of help us out. So maybe we don't add those in right now. Let's talk about them just in a couple minutes, okay? So make sure you have this written down. 1 standard deviation above and below is 68%. 2 standard deviations above and below is going to be 95%. And then 3 standard deviations above and below is going to represent 99.7% of people. So let's actually use that to analyze some data. Okay, so they're telling you that you had a normal distribution. Okay, so that means it's going to make this bell shape, and it has a mean of 21 and a standard deviation of 4. And then you're asked to answer some questions about it. Okay, so what I would like you to do is I want you to create your normal curve here. So we start off by our middle, right here at the middle. What number would go there? Think about it. It's going to be our mu, our mean, and that's going to be 21. Now, if we come out 1 standard deviation in each direction, okay, remember that's going to be our middle part, and the middle part is worth 68%. And you can look back at your notes. You don't have to memorize this, okay? You have notes for a reason. That's going to be 21 plus 4, or 25, and 21 minus 4, which will equal 17. Now that represents 68%, but let's say we want to go out to 95%. That's 2 standard deviations above or below. So I would do 21 plus 4 again, which is going to give me a 29. And I would do my mean minus 4 again, which is going to give me 13. And that's going to represent 95% of people. And then lastly, I could go out 3 standard deviations, and you could go out further, but really people don't go out further because this is going to represent 99.7% of the people that were involved, or the data points involved, okay? And that's going to be if we go backwards 4 and 4 and 4 more, or forwards 4, 4, and 4 more, okay? So let's answer these questions, and I think this will make a little bit more sense. So it says, find the range of values that represent the middle 68% of this distribution. So if I want 68%, I want from here to here, right? Well, those are going to represent all the values that are from 17 to 25, right? 17 to 25 is going to give me 68% of that curve. And that's the range of values, okay? So that's interesting. If you want to get a little bit more than half of your people, right, and you want to get the middle half, right, the most popular, your highest bars, you would look for the data that was from 17 to 25, okay? So now it gets a little bit tricky, alrighty? So let's take a look at this next problem. And like I said, this one actually is pretty darn tricky. It says, what percent of the data will be greater than 29? Okay, so greater than 29. Let's come over here. I see 29's right here. Boom. And they want to know, or I need to figure out, what the heck is that? Okay, that is the percent. Percent is the area under your curve. Okay, this is going to be the percent that's greater than 29. Now you might say, oh, 29 is 95%. Well, it's not. Okay, from 29 to 13 is 95%. So what that means is everything that's not from 13 to 29 is the extra 5. So that means this little area here and this little area here, if we add those together, okay, they would have to equal 5%. Now, I want to remind you why, okay? If from 13 to 25 is, or excuse me, from 13 to 29 is going to be 95% and this whole curve is 100, then I would do 100 minus that 95 to get me to the 5%, okay? So that helps me a little bit because now I know that this chunk right here is one of the two tails. So I'm going to take that 5%, I'm going to divide it by 2 because I don't want both little tails here. I don't want both ends. I just want this one end. So I end up getting 5% divided by 2, which is 2.5%. Okay? And those can be kind of tricky, okay? I would encourage you again. That's why I'm having you make this graph, right? I want you to shade it. I want you to think about it, okay? Find the numbers that they're referencing. Let's take it one step further and apply it to a survey that maybe was conducted. So let's say they looked at the height of 1,800 adults and they find that it's normally distributed and they have a mean of 70 inches tall with a standard deviation of 2 inches, okay? So that means the average person is 70 inches tall with a standard deviation of 2 inches. Okay, now it's not 5 inches, it's not 1 inch. If it was 5 inches, our data would be more spread out. If it was 1 inch, it would be even more clustered than it already is. So let's make our normal curve. Right through the middle, we always put the mean, and our mean here is 70. Then we're going to put our standard deviations, reminding ourselves that from here to here is 68% of our people, okay? So I'm going to use my standard deviation. I'm going to add standard deviation once to go 1 bar away, and so that brings me to a 72. And then I'm going to go 1 below, which brings me to 68. So I want to remind you what this means, folks. That means there are 68% of men that were surveyed are between 68 and 72 inches tall. That's what this means. 68% of the people surveyed were between 68 inches tall and 72 inches tall. If we want to get even higher percentage, we'd go out another standard deviation, right? So it was add 2, let's add 2 more. This was minus 2, let's minus 2 more. And this is going to represent, yes, 95% of the people. So 95% of the people surveyed are between 66 and 74 inches tall. Then if we want to get virtually everybody, okay, if we want to get that 99.7% of people, okay, then I'd go 3 standard deviations out. So I add 2, and I add 2 one more time. That's going to be 76. I minus 2, minus 2, minus 2 again. That's going to be 64. So 99.7% of people in the survey were from 64 inches tall to 76 inches tall. And hopefully that makes a little bit more sense the more that we apply these percentages to the numbers on the bottom, okay? So now they're asking us, let's take a look at our questions, about how many adults were between 66 and 74 inches tall. So between here and here. Well, that's pretty kickin'. Look, it represents our 95%. Now you're like, sweet, we're done that problem. I want to slow you down. The question isn't what percent of adults are between 66 and 74. They're asking how many adults, okay? So I need to figure out 95% of the amount of adults that they surveyed, and they surveyed 1,800. How do we go about finding percent of a number? Percent of a number. Well, we can't calculate with percents, so we change them to decimals first. So I'm going to move this forward 2 spots. I'm going to make it 0.95. And the word of can mean 2 things. It could be multiply or divide. In this instance, we're going to multiply. So we're going to find 95% of 1,800. So let's go down to our calculator. I don't really want to use the graphing calculator. And I'm going to do, I know I could have just typed in what I wanted to, 0.95 times 1,800. And I get 1,710 people. So that's how many represents that 95%. 1,000, and I lost it. What was it? 1,710. So make sure you're careful with the question, right? They're not saying what percent of adults, that would be 95. They're saying how many, so we have to do 95% of the entire sample, okay, which was 1,800. So we change it to a decimal and multiply. Okay, and if you look, that number makes sense, right? That's almost everybody. It's 95%. That seems about right compared to the total. Next, they ask, what is the probability? Now, probability, you've seen it, can be theoretical or it can be experimental. In this case, it's kind of experimental because it doesn't have to model this curve exactly. But probability is also represented as a percentage, right? So really, when they say what probability, you could change it to what percent chance is there that a random adult is going to be more than 72 inches. So we're going to come up to 72, okay, right here. And if they're more than 72, we're talking about this area in our curve. Boom, just like that, okay? So we can use some of this information here, okay? I know in order to figure out this area, folks, I mean, I guess you could kind of try to figure it out without. I would take this chunk away from 100, okay? So this 72, if you think about it, is the side of the 68. Now I could subtract 68 from 100, that's fine. But really, what I want to do is I want to say, okay, this whole half of my curve right here represents 50%. So I have 100, and I'm going to start by subtracting off that 50% for this orange chunk right here. None of that is going to be in my area I want. So that leaves me with a remaining half. Now from that half, I don't want this piece, okay? And if you remember, this middle part is 68, right? So that means this one little part here is 34. So I'm going to take that 50 and I'm going to minus off a 34 again. So 50 minus 34, I could do it the traditional way and get 16. So there's a 16% chance, okay, because that's the percentage that's left in this little tail over here. There's a 16% chance that a random adult is 72 inches or taller. So it's important for you to note that if they're asking you for a probability, not percent, it should be inches or taller. If they're asking you for a probability, they also are referring to percent, and both of those things are the area under your curve. So you might have to kind of do here, right? Subtract from 100, okay? You might be like, couldn't I have just figured out this half? I mean, I guess you could have, right? If you knew this half was 50 and you knew that was 34, you wouldn't have had to subtract that piece off. You could have done just 50 minus the 34 from the get-go. There are several strategies to start attacking these, but you have to use this empirical curve every time. So if we take a look at your assignment tied to this, let's see, here, okay? Here are the notes and the examples. What you're going to do is you're going to get 2 more word problems. So what I'd like you to do is first off complete your normal distribution, okay, using the empirical rule. Then you're going to answer questions like we just did. And then you'll have another one where you're going to fill out your curve first and then answer a couple questions like we just did about that. Okay, take your time on these. It's out of 10 points. Again, this is going to be your only assignment this week. You're welcome. Happy Memorial Day. I hope you enjoyed celebrating it with your family. And that's all I got for you. If you have any questions, you can feel free to reach out to Mr. Andreessen or myself. Y'all have my email. It's mwhite@winthropschools.org. All right, folks. Thanks for hanging out with me today and learning a little bit about the normal curve. Bye.